So these are, once again, announcement on final exam. Just make sure that you come at the exact time. And the coverages from chapter 6 to 11 is SAP op-amp circuit. And we'll focus our questions on bipolar devices, MOSFET, sorry. Except bipolar, that means that we're going to focus on mostly MOSFET circuits and also MOSFET devices. And there will be, I will give you more detail. The plan for today is that we're going to sort of wrap up all our discussion on frequency response today. So on Thursday, I'll probably just give a discussion session, probably a few exercises that you come up. And we can do a discussion and some review on finals. So more details on finals will be available on Thursday if you're interested in knowing what type of question might come up in finals, okay? Any questions on plans? So today we're probably just going to finish up all of discussion on frequency response, okay? So the plan, okay, so what we have already discussed are we're going to do frequency response of single stage, of course, single stage. Yeah, since we're only going to focus on MOSFETs, so it's going to move along much quicker, only one type of device. So there's, of course, three types: common source, common gate, and common drain, which is source follower. So I'm going to quickly review the one that we have already discussed. It's the common source configuration. So if only, I'm going to focus on only the impact of parasitic capacitance now. So we're only looking at high frequency domain. Those are the parts that we have not yet discussed. For low frequency, those are external capacitance. They mainly have the same effect on each one of the stages. So the main difference on these three types of three type of architectures mainly on is parasitic capacitance, the impact of parasitic. So let's look at common source configuration. So if you have a simple common source stage, and your circuit looks something like this, VDD. So this is without external capacitance. We typically want to add a source resistance, and this is always there. So anytime when you connect it to an input stage, there will always be parasitic resistance in your wires. So this will be my input. This will be my output. So in a transistor model, M1, we know that there's, we're not going to draw the small signal model. Now we can simply add our parasitic capacitance, since we already know that there's CGD and CGS. Okay? So we know that this can be equivalent. The way to analyze this is through Miller approximation. Once again, this is the approximation just to simplify our analysis. So the way to do this is then your circuit can be equivalent to this. The way to look at it is that it would then have a C1 and if I want to be more precise, just so we be more precise, there's also junction capacitance drain to body. Okay? So I can lump them into input terminal and output terminal. The effective capacitance, there's only two nodes. So the way to think about this is that I want to see what is the effective bucket I only have two nodes. So I'm summarizing the effectiveness of the movement when I charge up, when I pull in water, when I charge up the node. How fast can it go? The effective way of doing that is just to give an effective capacitance. Not a real capacitance, it's an effective capacitance. So sort of like you observe the behavior of these nodes and then give an effective capacitance to this particular node. So input and output, there's only 2 nodes, right? So then in this configuration, once you have this equivalent circuit, then we can construct a C1, C2, and then it will give you 2 poles, input poles. So if I want to construct the transfer function, once again, you have a low frequency. In this case, because we don't have, we skip the analysis of external circuits. So at lower frequency or mid-band where your signal is actually passing, we know that its gain transfer function can be written as its original gain, GMRD, plus 2 poles. I have 2 poles. Omega P1, 1 plus J omega P2. So I have 2 poles. One is omega P1 is RS input pole C1. Omega P2 is RD, output resistance times output terminal capacitance. So then you need to construct what actually C1 is composed of. So C1 is composed of course, you have its original CGS. You have a capacitance. And then there's Miller capacitance. CGD is being amplified, effectively amplified by this non-inverting gain. Inverting gain, CGD. So because of the inverting gain, the opposite side is sinking. Therefore, it's very hard to pull your input node. So from output terminal, you have this parasitic capacitance, and then there's also Miller capacitance. Okay? So these are how you determine the input and output terminal and its the effect of parasitic capacitance, and it'll lead to 2 poles in the system. Okay? So in terms of transfer function, if I give you this transfer function again, you should be able to construct the Bode plot of both the phase and gain. The other thing we're going to look for, remember when you go back to understanding a transistor, understanding a single stage amplifier, there's 2 things. One is its gain. This is if you consider frequency response, this is the overall gain. Input, output, the ratio between input and output. The other things we're concerned about, of course, is impedance. Instead of resistance, now we're going to look at impedance. So if I want to find out, instead of gain, this is only 1. Remember, anytime when we characterize an amplifier, you also want to look at impedance. That's input impedance. By definition, that's Zn. The way to do that, you can also still look at Vx, Ix, assuming that the same definition, you can do that on based on the same analysis. The only difference is that we're going to add the impact of capacitance. Okay, so in this case, remember if you have a common source amplifier, every time I ask you for input resistance, you're happy because it's infinite. You don't need to consider. But in this case, now we need to consider charging current. Previously, the reason why you have an infinite input resistance is because you only consider DC current. We have an insulator from the gate, therefore there's no current, no DC current. But now we need to consider charging current, therefore your input impedance will be very easy. If you look at this, it's 1 j omega C1. Okay? So that's your input impedance. And based on this, you will see that if I want to plot this, the gain, or the impedance as a function of frequency, what it will look like. For input impedance, I meant looking in from here. This is typically from the source, so you don't really consider that a part of your amplifier, Zn. Okay? So from Zn, I'm only having, if I ask you to plot this, this will look something like this. It will have a 0, right? This will be my impedance as a function of frequency. Okay? So if I ask you to plot this, one of the important things is that you want to see when your impedance doesn't really actually, you can have set a value, typical, what is the type of value that you want. So you need to highlight it with a particular level. It's not necessarily 0 or 1. It doesn't actually mean, because there's a unit to that. This is in the unit of ohm. Okay, but intersecting point would then highlight the levels of your impedance. But the basic idea is that you will see that as frequency increases, these charging current typically increases. Decreases. Input resistance. We know that for an amplifier circuit, if your input resistance decrease, that means that remember, we'll go back to voltage amplifier. What you want for an ideal voltage amplifier is to have infinite input resistance or input impedance. But in this case, as frequency increases, the effective resistance reduces because of the charging current, then it actually means that your gain, typically you will see gain degradation as a result of input resistance, input impedance, the decrease of input impedance. That's typically this is actually what we see from pole 1. This is the same thing. But from impedance point of view, this is the results. Okay? So for a common source stage, I would like to go through an example. I have an example. So let's consider an example, something like this. It's like this is a MOS common source stage with diode connected I don't know if you remember the benefit of having, this is not it. So let's consider a circuit like this and do this. You can do it in various ways. We can do it both MOS with the diode connected or PMOS with the diode connected. I'm going to do a PMOS version with the diode connected. Okay? So if this is the case, if you simply bring in the parasitic capacitance, and then you can also ask you to find is omega P1 and P2. So I have output, let me do the same plot. Let's say if this is my circuit. And I'm also adding RS input. So my input come in at the source, at the gate, Output at the drain. I have two devices, As I said, there's two ways of realizing diode connected. You can use two NMOS. Our previous examples are using two NMOS. You can also use PMOS and diode connected. This is called diode connecting because the reason why it's called diode connected is coming from bipolar, because when you have base and collector shorted, you only see a diode. That is why it's called diode connected. And it has been used for MOSFET as well. When you have gate and drain shorted, that's called a diode connected. So let me highlight. This is typically referred to as a diode connected load. Okay? So for this type of circuit, the way to analyze it, if I give you a parasitic capacitance, the level of all the parasitic capacitance, you should first realize where it is. So I have this CGS1. Because there's two transistors, so you want to be CGD1. And there's CDB1. That's from transistor number 1. That will actually come into play in your circuit. And then let's look at transistor number 2. For this case, you don't have a CGD because my gate and drains are shorted. But from this terminal, you actually see a CGS, right? CGS2. And then from this junction, this is also the drain junction. The drain junction will still have a CDB, drain to body, number 2. Okay? So I'm not going to do the equivalent. So we're going to also look at the input ports. So the input capacitance, you could input, let's define C1 as this input terminal, terminal number 1, terminal number 2. So C1 is Cin, which will be CGS1 plus CGD1, 1 plus GM. Now, what is the GM1? What is the gain of this particular circuit? GM1 times what is its output resistance? Diode connected is, remember? This will be in the exam. I glanced at the finals. So make sure you know. There's no RO. Yes, I got, what is it? Correct. So this is very important. When you have a diode connected, you can do the exercise on your own. If you have a diode connected, it basically means that your gate is connected to drain, meaning that whatever you're giving the control, you're actually seeing the main current with the transconductance current. So that's when you get, let me just highlight it over here. This is GM2 over 1. So the resistance, effective resistance you're seeing at this terminal, you ignore output resistance because this is much, much smaller than output resistance. This is assuming that RO1, RO2, both are smaller than GM over 1. That's mainly true in most cases. Okay? Okay? So then, M plus CDB1 plus CDB2. This is a bit tedious, but you need to get all your parasitic capacitance, see where they come from, and then lump them together. So, sorry, this is for output terminal, sorry. So from input terminal, you only see CGS and the Miller capacitance coming from the amplification effect. And then for a C2, will be at the output terminal, would then be, I moved too fast. There's 2 drains connected to the output. So there's drain to body, and then because these terminals are short, so you have an additional CGD2. And then I also have the Miller effect, CGD. 1 plus GM1. The gain of the circuit is GM1 over GM2. Okay? Okay, let me sort of explain. These are coming from M2. This is the parasitic from the output terminal, the same as our previous case here. CDB, drain, junction capacitance. And then this is Miller from, feed-forward from M1. Okay? And this is also Miller at the input terminal. Miller cap from M1. Okay? So you should be able to get these capacitance, and then your poles should follow these rules, right? So let's write down the poles. So if I ask you to find the poles, omega P1 will be C1 RS. Let me use RC. Source resistance C1 over 1. And omega P2 will be a high frequency pole because your output resistance will be R out C2. If you want to be precise on your output resistance in this case will simply be RO1 in parallel RO2 in parallel 1 over GM2. So that will be approximately the smallest resistance dominate. So it will be 1 over GM2. Okay? So this can be approximated as GM2 C2. Anytime you see a pole or zero at this type of expression, it's typically a high frequency pole because 1 over GM is a low resistance, low impedance, meaning that it carries large current, transistor charging current, so that it's a fast moving node. It could be much smaller if RS is high. Okay? Okay, so we sort of finished our first circuit, which is a common source stage. And then we're going to look at common gate. So for common gate is fairly unique. One of the features of common gate, I'm just going to draw a circuit. So for a common gate stage, you do the same thing. You draw the circuit first. I have a common gate stage. Remember something like this. And typically what we have is that you connected to there's always a source resistance to set your input pole, and output resistance RD is to set the output pole. So you're always looking at node 1 and 2, input and output. For a single stage, there's only 2 nodes. So it's fairly straightforward. I have this is VB. There's a fixed, let me use V gate. So that's a fixed DC bias. It's a AC ground node. So if you look at, so once we have this, you simply insert your parasitic capacitance. Let me use yellow. So if you look at a transistor itself, remember the model, there's source to body, source terminal to body, these are junction capacitance. Drain to body, so drain to body, there's also these are junction capacitance. And then I have CGD, and then I have, let me move the node. So that my CGS, okay? So I have input node, node number 1, output node, node number 2. That will simply introduce my poles, 2 poles. So if you look at this circuit, there's no Miller capacitance. What are the main feature of a Miller capacitance is that it feed from 1 to 2. There's no direct capacitance between 1 and 2, between source and drain. They're isolated. Therefore, you only see 2. If you look at this is ground. This is AC ground, right? So if you look at this is viewed as AC ground. So all your capacitance are grounded in the other terminal. So if I want to do C1 for node 1, input node, my C1, the total capacitance will be CSB, junction capacitance plus CGS. This is grounded. So these 2 capacitances are in parallel. You simply add them up. Okay? From output terminal, it's the same. I start with my junction, drain to body, plus the parallel plate capacitance CGD. So this is node 2. Sorry. Let me add it here. So the key feature I want to highlight is that there's no, as I said, no feed-forward. No feed-forward cap. So there's no Miller amplification. It will actually make our analysis much easier, and it would actually make your estimation much easier. Typically what happened, let me just write down. So for node 1, it would then introduce omega P1, which would be determined by input resistance. If you look at input resistance, it will be RS in parallel. Remember, input resistance of a common gate is what? Go back. What is it? Correct. In parallel RS, because I have an RS, that's my input resistance times capacitance, so C1. Let me just use C1. We already know what C1 consists of. And then there's, from node 2, you get omega P2, which will be mostly RD times C2 over 1. Okay? So typically, if you if you want to compare frequency response of various circuits, common gate stage are typically viewed as a high frequency circuit. The main reason is because it has no Miller amplification, so it only being limited by these parasitic capacitance, and also because of this. This will actually have a high frequency node because my GM, anytime you see, let's say if RS is larger than 1 over GM, remember anytime you see a pole at this particular, if you go back to look at our transient frequency is GM and parasitic capacitance. So this is already approaching your limit. So this is typically viewed as a high frequency pole. anytime you see GM, it's a high-frequency pole. So you already have a very high-frequency pole. That means that you don't, this is typically where you set your bandwidth. So you actually have a overall better frequency response circuit if you're using common gate stage. And this is mainly because of this effect. No feed-forward capacitance. Okay? So let's do an example as well. So let's to get a sense as to of a common gate stage. So in this case, I'm also using the worst case scenario, which is, the reason why it's called the worst case scenario is that it actually has the highest parasitic capacitance. So I'm going to use the diode connected again example. This would then actually give you the highest capacitance, parasitic capacitance in the circuit. So let's just use the same architecture. Instead of having a RD, you're using a diode-connected load. So this is my VL. Again, RS Vin. And this is at a fixed bias VG. Okay? So anytime you do this analysis, you want to make sure that you get all your parasitic capacitance. Just make sure that you know that each node would then contribute to different parasitic capacitance. Let's just add them. I have yellow. Let me get different color. So we're going to add them back because there's two transistors. So M1, M2. So there will be, once again, input pole, input terminal, source to body. There's one transistor, and there's CGS1. This is also ground, remember, AC ground. So let me just make sure that it's AC ground. Everyone knows that. And then from alpha terminal here, we have CDB1. This is from transistor number 1. So transistor number 1 contribute to, four terminals. So there's another CGD1. Okay? So for the PMOS, again, because I short gate and drain, so you only see this. This is CGS2. And then at the upper terminal, you also see CDB2. So these are the two capacitors that can be, as we have did in the exercise, these are the two capacitors contributed by the PMOS, diode-connected PMOS. So what we need to do now is just to find out C1 and C2. So C1 will be only two components. One is this junction capacitance plus CGS1. From C2, there's many more because there's junction capacitance, two junction capacitance, CGD2 plus CGS2. Sorry, let me just be precise. I'm separate them into type of capacitance. You start with junction capacitance. Because source and drains are junctions, they always come with junction capacitance. And then parallel plate capacitance, gate oxide capacitance, related capacitance. Okay? So once you have these, Let me give some numbers so you get a sense as to what are the typical values. So if I give you some numbers, you should be able to calculate poles, omega p1, omega p2, okay? So let's say, let me give parameters. RS, let's say it's 200 ohm. And our diode-connected load with GM1 equals to GM2 equals to 6.7 milliamp per volt. Okay? So I have, for both transistors, CGS1 equals to CGS2 equals to 250 femtofarad. Once again, the typical parasitic capacitance, as I already alluded, that in advanced technology, for example, you probably have something in a 10 micro, let's say 0.18. If you're using 0.18 micron technology, your Cox is at a level of approximately 10 femtofarad per micron square. So your typical values are in maybe tens of femtofarad to 100 femtofarad. If you ever calculate your parasitic capacitance, let's say for nanoamp, those are nanofarad, those are big capacitance, nano or microfarad. If you ever break down a motherboard of your computer, you see those big capacitance, those are in the unit of millifarad, micro or millifarad. So these are large parasitic, we call passive devices. But parasitic capacitance are typically in the range of femtofarad. If you want to make them into picofarad, you need large area to sustain these large capacitance. So picofarads, you have to deliberately make them. Parasitic capacitance in the unit of typically less than 1 picofarad. Okay? So just to give you a sense. So for C, and I also have CGD, which is about 1/4 of our the CGS. We're going to assume that both devices have the same parasitic capacitance. And then we have junction capacitance. That's 100 femtofarad. Because source-drain junctions are symmetric, so that we're going to assume that they're having the same capacitance. So if that's the case, I should be able to calculate my C1 and C2 respectively. So my CSP, this is 100 plus 250, that's 350 femtofarad. C2, then there's 2 junction capacitance, therefore it's 200 plus 250 plus 80. I get it right. That's 530. Once we find these parasitic capacitance, the next thing we can do is to find its frequency. So omega p1 will be approximately, input pole will be 1 over GM1. So I could do C1. As I said, 1 over GM in parallel RS. Okay, you simply insert the numbers, and then this will be somewhere around 34 giga radius per second. So this is already a very high frequency pole. And then omega p2, as we already know that output resistance is 1 over GM2, so it's GMC2. And this is approximately 12.5 giga radius per second. Okay? So you can see that all these poles are at relatively high frequency. So this is the main characteristic of a common gate stage. You typically have high high-frequency poles that will make the overall circuit exhibit high-frequency response. Okay, good. So we're moving on to the last one, a single-stage amplifier, which is the follower circuit. So already you have the feature. I want to emphasize once again, for common source stage, you have Miller amplification. So typically your dominant poles are at input pole because this has a much higher capacitance in most cases. In common gate stage, there's no Miller amplification, so you have basically the same loading on nodes. Input and output node are basically the summation of parasitic capacitance. So these capacitance are comparable levels. Therefore, your poles are typically at comparable levels, and typically at a fairly higher frequency regime. And then lastly, we're going to look at follower circuit. Let's see if I have enough time. So let's look at follower. So for source follower circuit, once again, you start with your low frequency version. Okay. So let's assume that it's being biased by a current source, so I can set. Typically, this is what's being done. Biasing my circuit with a current source to set GM. I1 is to set the transconductance of M1. Okay? And because this type of circuits we're going to add the external capacitance in this discussion is because the main purpose, as I said, what is the main purpose of a source follower is to either drive a low resistance or high capacitance. The main purpose of a follower circuit is to provide current to drive a node. And this is very, very commonly seen, especially in internal circuit design. What you typically encounter are large capacitance. For example, if you ever take courses in CMOS image sensor, for sensor circuit, you all have a digital camera on your phone. Those consist of billions of pixels, and these nodes are typically consist of large capacitance. So we're going to add these capacitance, and this is very commonly seen. So we're going to add this external capacitance. These are external capacitance, and this is the main purpose of a source follower circuit, as I said, to drive large C load. Okay? And then we can add a parasitic. So there's two. There's CGD. And there's CGS. Okay? So in this case, we'll then encounter two parasitic capacitance. Let's just, we're going to ignore the source-to-body capacitance because this is much, much larger than all the parasitic. These are much, much smaller. So I'm simply going to ignore that. This is a large capacitance, so if you consider the C as B, can be typically ignored. So we're going to only consider the effect of these three capacitance in the source follower circuit. Okay? So first of all, you want to identify that now, let me highlight. I want to identify that now you don't have, your CGD is grounded at one terminal. This is input. This is output. Okay? So consider this This is a grounded capacitance. So simply contribute to your input terminal. But what about CGS? CGS is now the feed-forward capacitance, right? So you have a CGS become the feed-forward. But this is somewhat different from our common source amplifier. If you think about a common source amplifier, it has first of all, it has a non-inverting gain. Meaning that if you think about the effect, it's also subject to Miller effect, but it's actually in a good way. It actually reduces the effect of CGS. The way to think about this is that when we talked about Miller amplification, the main reason for the input node, very hard to pull out the input node because your opposite sides are syncing. But in this case, remember, it's a follower circuit. What it means is that if I'm moving in this direction, my output node is moving in my same direction. So it's reducing the voltage I need to apply across this capacitance so that I will see a less capacitance effect. It will then reduce CGS effectively. Okay, so we're going to look at how to determine. We're going to talk about that when we talk about impedance, but let's just do the transfer function of this particular circuit. So to do that, the best way to do this is this. So in this analysis, in order to make our life easier, I'm going to ignore, so we're going to ignore. Ignore CGD. We're going to assume CGD is open. So we're going to ignore the effect of CGD. So I'm going to only see CGS, GM. So that will be my equivalent circuit. You first construct the equivalent circuit. We're going to ignore CGD and RO, the effect of RO and CGD for this analysis. And because my drains are grounded, this is common drain. Okay, let me highlight the input and output. My input come in at the gate. Output follows at the source. Okay? I don't think I have space or time for the analysis, so I'm going to keep this page, and then we'll take a 10-minute break. We'll come back and then do the analysis on a source follower circuit. Both the gain, transfer function of the gain, we're going to find out three important things. One, transfer function, input resistance, input impedance, output impedance. All of them are a function of frequency. So these are the three things now we need to construct once we analyze single-stage amplifier in frequency domain. It's response in frequency domain. Okay, let's take a break for 10. Good. 我刚才稍微讲一下，就是礼拜四我在想说，我今天应该可以讲完所有我想要 cover 的内容，所以呢，礼拜四的时候呢，大家就可以来问问题。如果你有问题的话，如果你没有问题，我就可能像上次一样给一些题目，你可以来作答。然后我们好像已经加分很多，是我们发糖果嘛？我不知道，就是做一个那个 review exercise 这样之类的东西，好不好？那就是如果大家有什么问题，然后我过去有办过，以前那个叫什么？以前就是 online 的时候有办过那种讨论会，就是说第一个就是大家可以听一下大家的 feedback 针对这个课程，所以我们最后一节课就是会比较就是不会讲课程内容，就课程内容我大概今天会讲完，所以最后一节课就是来回答一些问题。如果你们没有问题，我就问你们问题嘛。那如果你们有问题，你们就问我啊，对不对？就是 discussion 的 这个，然后另外呢，就是我们也不一定是要问课堂上的问题。那有时候有同学有一些什么人生的迷惘，不就是修课啊，或者是选领域啊那种东西，有一些这种问题，那我们也可以一起讨论这样子。那也可以讲中文没关系，我们礼拜四可以讲中文。好，那大家就这样子。好，所以我礼拜四我们就是我觉得我应该可以讲完啦，所以我们就礼拜四就是一个比较开放的 session， 这样就是 discussion session。好，那也不用上到2个小时，如果大家没问题，我们就提早解散。 Okay, let's continue our discussion. So what we're going to do is to wrap up our last circuit, which is the source follow circuit, and look at its unique. It has a fairly unique transfer characteristic, and also has very unique, we call the impedance effect. So it has a very strange output impedance characteristic that will simulate something called an inductive load. So we're going to look at that in a bit. So as I said, if you want to construct a source follower, the transfer characteristic of the source follower circuit, what we do is to consider only two capacitance, the main capacitance. We're going to consider only CGS. We're going to explain it later. And this is the loading capacitance. The reason why it's kept in this discussion is because this is what the main operation or main usage of this type of circuit are being applied to. Source followers typically apply, as I said, to drive large loading capacitance. So if this is the case, let's construct its output resistance. So if you look at transfer function, look at its input is equals to VGS plus VL. And what is VL? VL will then be, VL can be determined by the current flowing to loading capacitance. So there's two current. One is GM VGS. That's the main transistor channel current. The other is charging current coming from capacitance. So there's two branches of current. If you look at the current going through C load, there's two. One is transistor channel current. The other is coming from CGS. That's the charging current. And this is the current times its resistance. So it's on this J omega C load over 1. Right? My output resistance is this. And then I could rewrite my characteristic would be J omega C load GM plus J omega CGS, just so that I didn't miss anything, VGS. So you want to express your output in terms of VGS, express your input in terms of VGS. So then, if this is the term, my output will be VGS 1 plus VL. So this is J omega C load GM J omega CGS. Okay? So I'm simply moving the V out upwards. So I can get V out and V in all in terms of VGS. That's the best way to get your transfer function. So my transfer function will then become V out, by definition, V in, and is equals to, from the denominator, there's additional 1 term. So it's 1 plus GM, 1 J omega CGS over J omega C load. And there's the same term. Okay? So you can make some arrangement by multiplying both the numerator and denominator with a J omega C load. So this would then become GM J omega CGS. This will be 1. There's no 1, sorry. There'll be a GM plus J omega, let me be precise, CGS plus C load. Something like that. Okay? So as we already done in most cases, we want to make it in a term as zeros and poles. So if you do some rearrangement, divide both term by GM, you get 1 plus J omega omega Z. There's 1 pole and 1 0 in the transfer function of a source follower circuit. Okay? I have omega, let me write it down, omega Z at GM CGS. I have omega P at GM CGS plus C load. Okay? So can you tell me which one had a low frequency? Which one has a low frequency? Poles or zero? That will determine the shape of your Bode plot. Okay? Let's do the Bode plot over here. So we're going to do this as a function of frequency. And also we're going to do the omega. Okay, anyone wants to do the plot? No? I haven't prepared my snacks and stuff. Okay, so to answer the question, first of all, which one is a low frequency? Poles or zero? That should be zero, right? Which one is pole? Yes, correct. Omega P. We already know that omega P, in most cases, C load, this is loading capacitance much, much larger than parasitic. So that means that my poles should be much, much larger than zero, right? Because it's driven by the same GM. So based on that, I should know that this is where my pole is, this is where my zero is. So you start with a gain of what? What is the gain? So you want to see the boundary. First of all, we want to look at omega much, much smaller than my corner frequency, which is the pole. If this is the case, then the gain, absolute value of the gain should be approaching 1, right? So you start with 1. And then we also want to know when frequency is much, much higher than 0, what happened, right? So when it's much, much higher than 0, let's look at the transfer function. Looks something like this. 1 plus omega Z squared. 1 plus omega P squared. Okay? So what happened is that this will be approximately as, you ignore the 1 because frequency is much, much larger than both zeros and poles, so that you get omega, and this come out of the square root, omega P, so it will be omega P, omega Z. This exercise just to tell you the boundaries. You know the turning points, and then you need to know the extremes so that you know how it turns. Right? So you set up the vertical boundaries, lateral boundaries, the turning points, and the extreme levels at very low frequency and very high frequency. So what is this? CP. This is actually CGS. CGS plus C load. Okay? I will explain what that actually means. So as I said, we already know where my pole and 0 is. And then we need to set our highest level. It's at 0 dB, which is 1. And then the lowest point is CGS C load plus CGS. So it's the ratio between its parasitic capacitance, CGS plus C load. Okay? So I know that at a very high frequency, this is where it should return to. And at high frequency, at very low frequency, you actually have a perfect source follower. It's an ideal source follower. It has a loading resistance. Your loading impedance is infinite. That means that you have an ideal gain, which is at 1. So if I want to draw my transfer function, so start at 1, and then once it hit omega p, it should be 3 dB, and then it should drop at a rate of, once again, 20 dB per decade. Okay? So as I said, you can double check because it's 20 dB per decade. That simply means that this distance, the ratio between these two, is the same as this. So how much it gains is equals how much it drops, right? So how much, the ratio between omega z and omega p, see, is the same as the drop in gain, the same ratio. Okay? And then it will flatten out because it hits 0. Once again, Bode rules start with 1, gain as 1, and it hits a pole, drop 20 dB per decade, hits a 0, return to flat. Right? So flat 20 minus, so it should be a minus. Okay? So this is actually our operation region. This is desirable bandwidth, typically referred to as a good bandwidth for my frequency, for my source follower, because I want to have an ideal gain of 1, right? So start to drop when the loading effect, I should say, loading effect of this capacitance become dominates, and you see the pole, and then start to drop all the way down to 0, to the 0, and then it'll flatten out. Okay? So let me highlight. This is GM, as I said, CGS plus C load. This equals to GM CGS. Okay? So if we do the phase domain changes, as I said, if you want to do the phase domain changes, you want to make sure that it actually starts to degrade or change within maybe 0.1 omega p to 10. So in this case, we assume that your poles and zeros are further apart so that it wouldn't affect each other. So it would then drop, starts to drop when it hits the pole, right, like that. Let me highlight. This is minus 45. And then in between, it will then hit minus 90. And then it will start to rise maybe close to 10. And then this is when I'm assuming poles and zeros are far away. This is the assumption. So that you should be able to identify, for example, if I ask you, what is the phase at omega equals to omega z? Or omega at phase at omega p? They both should be minus 45, right? If they're further apart. There's no interaction between the two. Or if I give you any frequency which is in between, that's minus 90. Okay? This is good. So this results actually give you something very interesting that I want to sort of discuss a little bit, is that when you have, what does it mean at very high frequency? So if you look at omega much, much larger than omega z, this means that you already sort of passed, remember the transit frequency, ft, of the circuit is approximately gm CGS plus CGD, right? So my omega 0 is larger than omega t. This is omega t, sorry. Just to be consistent. So that simply means that you already don't see the effect of transistor. If you look at the circuit, if I'm looking at the circuit, my small signal circuit looks something like this. CGS, C load. So at very high frequency, you don't actually see transistor. This is the main contribution from transistor, transconductance, right? So you modulate, and then the current changes. But now, at a very high frequency, you don't see this. So this is V in, this is V out. So if you have a circuit like this, CCS, C load, V in, V out. The gain of this particular circuit will then be CGS plus C load. CGS. Okay? You just say voltage divider by capacitance. So capacitance coupling effect will then simply give you this, meaning that your transistor will only become a capacitance, coupling capacitance, rather than having an active function, because it's way past its operating frequency. You only see this. That's why in extreme, you don't actually see, you only see the parasitic capacitance effect. Okay? It will be a capacitive coupling network, if you like. Okay? So we already tackled the first part. Let's look at its input and output impedance. So as I said, if you look at this Miller capacitance effect, if you look at this particular circuit, I have, if I'm looking at this, remember this is minus A1. So what if I'm having a positive gain? So the way to think about it is I have this. I have CGS. So the impact of CGS, instead of having a positive gain, I have a negative gain. Or if you think about it, let me explain this. If I have a Miller capacitance, which with amplification effect, this is when the opposite terminal is moving in the opposite direction when it's sinking. But in this case, because it's a follower circuit, so if you think about Miller effect, if my input is moving in this direction, my output is moving in the same direction. For example, if this is delta V, this will be delta V times its gain, right, voltage gain. And the voltage gain is close to 1, meaning that I don't actually need to supply anything. If I have an ideal case, this capacitance can be 0. The effective capacitance from the input terminal can be 0 because it's moving in the same direction. Okay? So it's, instead of having a sinking opposite electrode, you have a rising opposite electrode. So you have someone to help you. So that would then reduce the necessary charge need to be added on CGS. So the impact would then be your input. If I'm looking at that, my input resistance will be, I actually see CGD. I have, I'm just going to look at that example, CGD plus CGS. And this will be divided by, I should say, 1 minus A0. So what is my A0? My A0 will then, in this case, will be 1. If my A0 is approaching 1, this will simply be CGD. Your feed-forward capacitance, because it follows 100%, which means that I don't need to apply any voltage across. If my A0 is not exactly 1, then there will be an attenuation effect. It will then reduce the effective gain. If A equals 1, this is 0. So then you only see CGD. Your feed-forward capacitance can be completely canceled because it's rising. If both terminals are rising the same rate, there's no voltage difference required. Okay? That's, of course, the extreme case. Let's do an example on this effect. Get it. Let's say if I have a circuit like this, source follower circuit. Let's say, look something like this. This is more real. VG, input, VL. Okay? So my voltage gain in this case, M2. In this, let me add the parasitic capacitance. I have, once again, CGD1, CGS1. Okay? If I'm only looking at my input impedance, let's look at the input impedance. So if I want to look from here, from the input terminal, to find Zin as a function of frequency, will be you only need to consider charging current. That means that you only need to find out your input capacity, effective capacitance. So from this input terminal, Cin will be CGD1. That's this is grounded, one side grounded, and then Miller capacitance. That's 1 minus A voltage gain of the circuit times CGS. Okay, so the voltage gain of the circuit is actually, remember, is GM1, RO1 in parallel RO2, output resistance at this output terminal, 1 plus GM1, RO1 in parallel RO2. Okay? So if you simply insert that back in, your input resistance, input capacitance will be CGD1 plus CGS. If 1 minus this, you're left with this term, right? Let me write it down. 1 minus AV will simply be 1 plus your gain. Okay? So this will be 1 plus GM RO1 in parallel RO2. Okay? So if I have for example, if I give you a voltage gain, an example, if my source follower voltage gain is 0.9, this simply means that my input capacitance will be CGD1 plus only 0.1 of CGS. So instead of amplification, Miller effect can also attenuate or help you with reducing your input capacitance, meaning that your input impedance will simply be J omega C1. Okay? So this is actually good news because I could actually make a large capacitance, large transistors without increase my input resistance of my common source stage, because your common source stage is typically being driven with the previous stage. So you're actually reducing this capacitance effect is beneficial because you actually don't see that, you don't need to drive a large capacitance even with a large capacitor, a large transistor, because of this attenuation effect. Okay? So that's an additional benefit of using a follower circuit. What's follower circuit? Probably won't be. So lastly, we're going to look at, we already looked at our, again, the transfer function of a follower circuit, our, I should say, input impedance. Let's look at output impedance. So the way to think about it is that if I have a circuit, once again, like this, so this is my output node. I want to look at purely looking in from the source terminal, ZL. Okay? So I want to look at what is the effective impedance if I'm looking in from the source terminal of my follower circuit. And for this analysis, I need to add a source resistance at the input terminal, just so to get a benchmark at high resistance state, a high frequency state. Because we'll see why. So as our previous discussion, we're going to ignore, we're going to assume CGD and RO can be ignored. So let's draw our equivalent circuit and our test circuit. So if you look at it, it will look something like this. I have CGS, RS. Input is ground when I look at output resistance. So my equivalent test circuit, this is ground, transconductance, channel current. So my test circuit will be this, right? Given a test voltage, looking at test curve. By definition, ZL is Vx Ix. Okay? So simply, I'm just going to write down the derivation. Your current, there's two branch of current minus Gm VGS in reverse direction and minus J omega charging current. That's Ix. And then if you want to look at Vx, will be, let me highlight, this is VGS. Okay? So there's only one branch of current that's passing through Is, that's J omega. That's the same current passing through this capacitance. So my current, the voltage on Rs will be Rs times a current minus J omega CGS VGS. There's a voltage across Rs and also plus a minus another VGS. This is mainly because of the direction of my bias and current. Okay? So once you had that, we could actually construct our output impedance will simply be, after getting rid of VGS, let me just write down the results. It's Gm over 1 plus J. You can do the rearrangement. It's also come with the poles and a 0. So also, if you look at this, let me highlight the poles and 0. I have 0 at CGS RS. I have okay? So in this case, anytime you see GM over CGS, this is very high frequency. So in most cases, we're assuming that RS is much, much larger than 1 over GM, because that's the output resistance of your previous stage. Okay? So this will simply means that my 0 will be at a lower frequency and my poles will be at higher frequency. So it'll be an inverse of this response. Let me get rid of this. So again, if I ask you to plot the input resistance change, you also need the boundary. So I have Z out as a function of frequency. And we're only looking at its absolute value. Once again, in this case, it's opposite from our gain analysis. I have a 0 at a low frequency. So I have 0, omega Z smaller than omega P. So I will hit the 0 first, and then the pole. And of course, you need to find out the boundaries. Boundary is at low frequency. So you look at in region 1, this is region 1, 2, and 3. Okay, so let's look at region 1. At frequency much, much larger than omega Z, we know that this will equals to 1, so that your overall impedance is what we usually use at low frequency is approaching 1 over GM, right? This is our previous results, 1 over GM. And then at region 3, where frequency is much, much larger past the pole, past my transit frequency, what happened is that your ZL, if you look at this, will simply be GM1. This is the same as the previous case. Your omega Z will come out, omega P will come out. So it will be omega P against omega Z. So this is my omega Z. Let me just insert numbers. This will be GM, CGS. This will be RS, CGS. Sorry. 1 over RS. Okay? So you simply cancel the terms. I'm simply inserting my omega P, omega Z into the equation. So get rid of this, get rid of this, and then this will be Rs. Because we're looking at impedance, so your unit should be resistance, or in ohms, in the unit of ohms, right? It's 1 over GM. So 1 over GM, as I said, because we already assumed that 1 over GM is smaller than RS. So I start at 1 over GM. This is at the bandwidth that we wish to operate. And then once it hit omega Z, then your impedance will then start to rise. Omega Z, 20 dB per decade. And then it will hit, flatten out at RS. So what is the effect of this, or what does this response mean in circuitry? This is very unique. See, if you look at most of the architecture that we use, the impedance or the impedance at each node are typically at higher frequency, you actually see lower impedance. But in this case, at higher frequency, your output impedance actually increases. What are the components that actually have this characteristic? Does anyone know? What component that has, when frequency increases, its impedance increases? What? 电路学有教啊。What is this? What is this characteristic? If I want to substitute that with a passive component. No? No one knows? We know that for capacitance, when your frequency increases, your impedance reduces. What is the reverse? What is the opposite? What is the other one? 没人知道。除了电容还有什么 ？Correct. If you think about an inductor, well, we're not actually going to use an inductor, but this is a simulation of inductor. If you look at J omega L, if I have an inductor, the impedance of the inductor of an inductor actually is J omega L. So if you look at its impedance, as frequency increases, my Z load increases. That's the opposite of capacitance, right? So as frequency increases, meaning that the induced voltage increases, so that it would then lead to an inductive response. So this is we call the simulation of inductive response, right? So typically what we refer to, if you have this sort of response, this is, we call it inductive characteristic. In an integrated circuit, there's a two ways of realizing inductor. One is just build an inductor. And it's very costly and it's very hard to build inductors. So that you can actually use a circuit to simulate inductive characteristic. For example, if you want to build oscillator, everyone heard of LC oscillation. You want inductive components and capacitive components. Then this is the way of creating inductive components in using a circuit. So using a follower circuit, then sort of simulate the effect. Okay? Good? I still have 10 minutes. I'm going to talk about the last topic on single-stage amplifier, which is, I'm going to also, I don't know if I have an example. Let's go through an example of cascode. So let's look at the frequency response of a cascode stage. The main difference of a cascode stage and that of a common gate is that it will also have a feed-forward, but it will then have less amplification effect. Let's look at it. So I'm also going to use a loading resistor just to simplify our analysis. So remember, cascode is a common source plus common gate. RS, VG. Okay? So anytime when you want to analyze its frequency response as a result of, with the impacts of parasitic capacitance. Let's look at these. We're going to inject these parasitic capacitance ourselves. So there'll be M1, M2, just to make sure that you know what are the capacitance. So now I have this. There's a CGD1, right? But this can be through Miller amplification. I'm going to equivalent that by Miller amplification. And I'm going to explain why Cascode is also considered a good or high frequency circuit for high bandwidth design. It's beneficial for high bandwidth design. Let's look at the circuit itself, the parasitic capacitance. I'm simply going to look at the effect of parasitic capacitance. So if you look at CGD1, there will be C1, and this terminal will then introduce, I have actually 3 nodes, C2, and then C3. Let's highlight what is in each one of the nodes. For C1, I have CGD is CGS itself, CGS, right? So let me write it down, CGS1. And there's CDB1, CDB2, CGS2. Okay, so these are the parasitic capacitance we consider. Sorry, I misconnected this. Here, CDB2. Okay? So these are the capacitance I'm going to separate into 3 nodes. Input node, there's CGS1. And then, we're then subject to, again, if you look at this M1, at this particular terminal, because it's the source of M2, so you actually have, again, a 1 over GM1 times 1 over GM2. That's CGD1. So even though in the input terminal, I want to highlight this point is that even though this is being amplified, because this node does not amplify too much because of the low impedance at the source terminal, so that even though with an amplification is typically close to 1, so you only see twice the height, the level. It's not going to be maybe 10 times or 20 times as high. So there's Miller amplification, but it's gain because it's of a small gain, so that even though there's Miller amplification, you wouldn't see very high amplification effect on C1. And on the second terminal, the terminal 2 will be GS2. And then it will also subject to CGD1. And it will be, instead of, it will be the inverse of this gain. But it will still be a number close to 1. That will be my C2 and plus these, plus junction capacitance CDB1. Okay? So you see the gate, the Miller, and the drain. This source to gate. This one, and this one. 3. And for C3, that will actually be the high impedance node. So that will be CDB, junction capacitance, plus a Miller CGD. I'm sorry, CGD2. It's not a Miller, sorry, because this is grounded. So you only see this as ground. So both of them, these two capacitors are in parallel. Okay? So in a cascode structure, what will mainly happen is that I would then have most of them, all of them, all caps, are typically at a comparable level. Meaning that all of them are typically, does not range too far away. Therefore, you then have a wider bandwidth in most cases. Let me highlight the resistance of each node before we go. So for input terminal, let me write down the poles before I let you go. So there should be 3 poles because there's 3 nodes. So omega P1 will be C1 RS. Omega P2 will be dominated by GM2. It's probably too crowded. Let me move it to the back. So this would then introduce an omega P2, GM2, C2. And last one is omega P3 is determined by C3 RD, output resistance. Okay? Because the output resistance from the bottom is very high, you only see the loading resistance. Sorry. Good. Yeah. And this is the same. Okay? Okay? So let's break from here. Apparently, I haven't finished it all. So we're probably gonna do in half an hour wrap up for Thursday, and then we're gonna do the discussion. And you can bring up your questions. Okay? Prepare your questions, whatever. Okay, I'll see you on Thursday.